We've talked about the ideas of the chain rule a little bit in our investigation, and we got to a point where we figured out that the derivative of a composition is the product of two derivatives. But I want to talk about the other side of this, which is working with explicit functions and taking the derivatives in a very algebraic fashion. And it becomes just kind of like the product rule and the quotient rule, somewhat of a mechanical thing. You definitely have to pay attention to it. But it doesn't become too hard after some practice. But I do want to keep connecting it back to the concepts. So anytime the chain rule comes up when it's one function inside of another. In other words, when it's really a composition of functions. I take x squared, and then I take the sine of that. So this is of the form f of g of x, where actually, let me do g first. G of x is equal to x squared. That does the inner function. And I'm going to purposely use a different variable for the input of f, because it's very often very useful to have a name for the result of the intermediate calculation. And let's say f of u is sine of u. And the way this links together is that if we just say that u is the name for the output of g, in other words, u is x squared, then sine u does turn into exactly sine of x squared. The picture in terms of boxes and machines is we've got this g function which spits out x squared. We have a temporary name for that, which is u, which is going to be handy to keep track of how all these derivatives work. That goes into f, and that produces sine of u, which at the end of the day is sine of x squared. So let's look at one of the versions of the chain rule. It said if I have exactly this situation where I have an initial quantity, the intermediate quantity, and the final quantity, that's y, let's say, because I've got y up there, then the rate of change of y, the final with respect to the initial, this is where this notation really comes into its own, the dy dx notation. Dy dx is the rate of change, or how sensitive is another good way to think about it. How sensitive is the output of f, y, to the change in the intermediate quantity, times a measure of how fast that quantity is actually changing. In our example in the investigation, let me just compare this. We had temperature, big T, depending on a time, little t, and it was a product of how sensitive is the temperature to a change in position, which was given by dt ds, times how fast was the bug actually crawling along this rod. So that was the change of the final with respect to the middle, and with respect to the middle with respect to the initial. Okay, so how does that work out here in terms of this example? Well, we can calculate those quantities. dy du, that isolates the f part. It only talks about this equation. It says it doesn't have anything to do with how u is related to x or g or anything like that. It only says look at that outer function only and take the derivative of the outer. And so that's just f prime of u. And in this case, that's cosine of u. Now, in the end, we're going to actually want this in terms of x. U, for us, is really just a shorthand for the output of the inner function, the x squared function. So as soon as we take that derivative, we'll be able to plug that in. And so we get the outer function evaluated at the inner function, at the output of the inner. And this is one of the things that can be tricky about the chain rule, is you take the derivative of that outer function, and then you leave the inner function alone, basically. The sine of x squared has just turned into cosine of x squared. So that's not the whole story. That's only part of it. But that's one thing you do. So it's derivative of the outer with the inner left alone. All right, now what's the other part of the story? Du dx, that's the other part of this guy. Well, that's pretty simple, because that's just the derivative of g. U is just the name for the output of that inner function. And we're just taking the derivative of that with respect to x. And so that's going to be g prime of x, which in this case is 2x. And so the end, dy dx, the derivative of the whole thing put together, let me write that down, is just going to be cosine of x squared, that's derivative of the outer, evaluated at the inner, left alone, times derivative of the inner. In general, it's going to be the derivative of f of g of x is going to be derivative of the outer with the inner left alone times derivative of the inner. And that's the chain rule in terms of function notation. And it's the version of the chain rule that makes most sense to think of when you're talking about explicit functions like this. But when you're de-emphasizing sort of the theoretical aspect or the conceptual concept. Okay, so let's do another example real quick. So we're already up to 6 minutes. And let me just do one more notation here. Sometimes we'd like it's convenient to have a name for the whole function. Sometimes somebody might say, okay, let's call that h. And then this is just h prime of x. So the book often phrases things as they have two functions, and they make a composition, and they have a name for that composition. It's just handy because then you can just actually say, okay, what we're really calculating is h prime. So be aware of that. And hopefully we'll do an example of that in a second. One more example of... so let me do that in this style. Let's say h of x equals the square root of 3 plus 4x squared. And I'm going to think of that as an f of g of x. I see that it's one function put into the input of another. And that's a lot about the chain rule, is just recognizing that and being able to take functions apart into their pieces and recognizing when they're made up as compositions. And basically practice is the best thing for that. So here, it works. This is a composition if f of whatever we want to call its input, and I'll still call it u, is the square root of that input, and g of x is 3 plus 4x squared. And there's some leeway in terms of how much you could break down these functions. I could actually break down this function, g, into even more simple functions, like just the x squared function, and then just the multiply by 4 function, and then just the add 3 function. You only have to break it down into parts where you know the derivatives of each part. That's the point for us, is we just need to be able to do the derivatives. And we know how to take the derivative of this whole thing all at once. We don't have to break it down any further. So now h prime of x is going to be f prime of g of x times g prime of x. Okay, so what's the derivative of this guy? F prime of u, this is u to the 1/2, so it becomes 1/2 u to the minus 1/2. And the derivative of this guy, g prime of x, is just 8x. So here's f prime of g of x. That reminds us that this u would be a pretty acceptable notation, but we just want to remember that that's a shorthand for the output of g. And so that's going to be 1/2 times exactly what was inside f to start with. The key thing is it just sits there and doesn't change, really. And you differentiate f around it. But then don't forget that it does get differentiated, but outside, times 8x. And then it simplifies a little bit, 4x. And then we could rewrite it as an over the square root. But you could leave it as a minus 1/2 power as well if you want. So, a couple of pitfalls. You don't differentiate g inside here. It does get differentiated, but as a multiplier out here. You wouldn't put an 8x in here, for example. A lot of people think of it's just f prime of g prime, and that's just not right. That's a subconscious guess for it, but it's not right. So, let me stop there, and then I'll do another short one about a more graphical example.